An organic molecule with the formula C6H12O2 gives the following infrared spectrum and proton NMR spectrum. Identify the molecule that best correlates with these spectra. So if you were to encounter this question on a quiz or an exam, you would have options to select from. And I accidentally cut those off this slide, so we solved it without the options, and we can do that again here now. We have enough information with the formula and the infrared and the proton spectrum to propose a structure that is consistent with all of this data. So the first thing that I would do is I would look to the infrared spectrum to get some ideas of the functional groups that are possible. And I'm going to, of course, combine that information with the chemical formula. If a functional group needs an atom that isn't present, well, then it can't possibly be present. So I would look at the different regions of the infrared spectrum that we usually typically look at. So I would look in the CH stretching region, or just bonds to hydrogen region in general. And then the triple bond region, which we don't have any triple bonds, and the double bond region. So what I'm seeing here, the only bonds to hydrogen that I'm seeing are these peaks just below 3,000. So that's 3,000 there. So these are sp3 carbon hydrogen stretches. And that's not too surprising to see. If we look at the molecular formula, it's not completely saturated with hydrogen, but it's pretty close at C6H12. So I'm not surprised to see a lot of these sp3 or alkane carbon hydrogens. We should note that we don't see any OHs here. And so that's significant because with an O2, you could, in the formula, you could start thinking about, say, a carboxylic acid. But without that, we definitely don't have a carboxylic acid. We also don't have an alcohol. And there's also no sp2CHs. So if we have a double bond, it is not a carbon-carbon double bond. And we have no triple bonds. That's not surprising. I don't think that formula even accommodates a triple bond. But what we see here, really intense, is a carbonyl. And specifically this carbonyl, this is a little bit higher than what I would expect for an aldehyde or a ketone. Aldehyde, a ketone, definitely higher, or a carboxylic acid, definitely higher than an amide, but I'm not going to even write that down because I don't have nitrogen in my formula. So this makes me think that this is quite likely an ester. And that corresponds with this O2 as well. So it's really looking like an ester. The other functional group I would have considered with a formula like this is something like a carboxylic acid, but of course we don't have the OH stretch of a carboxylic acid. And if we look at the proton NMR, we also don't have the hydrogen of a carboxylic acid, right, which we would expect to see in this kind of region. And we also, while we're looking in this area, we also don't have an aldehyde. Because if we had an aldehyde signal, it would be there, right? So we don't have that hydrogen of the aldehyde. So really, really leaning towards an ester at this point. So let's start to draw that ester framework, right? So we've got something like this. We just don't know what's attached to these carbon atoms yet. And so this is the power of proton NMR. The infrared allows us to see that we probably have an ester. And so if we had a couple different esters of this formula, we could say, well, it's probably one of those. The proton NMR will allow us to say exactly which one. So in your proton NMR, you always see 4 key pieces of information from your proton NMR. You have the number of signals. So once we propose a structure, we want to make sure that the number of signals that we're seeing makes sense with the structure, that it's what we would have predicted or can explain it. So the number of signals, the chemical shift. And we already used the chemical shift when we said, you know, we just don't see anything in the range for a carboxylic acid proton or for an aldehyde proton. And so we already used that piece of information when we were eliminating those functional groups. So number of signals, chemical shift, the integration. So that can tell you the number of equivalent hydrogens. And on these small organic molecules, we can make some pretty simple conclusions with the integration. So when I see 2 hydrogens, for instance, I'm going to say this is most likely a CH2 group, because to have 2 identical hydrogens, they're probably attached to the same carbon. And likewise, let's look at the rest of these. When I see a CH3, the first thing I'm going to think is that's probably a methyl group. If I see 1 hydrogen, and this is a really messy 1 hydrogen, that's a CH. And the fact that it's really messy and split into a lot of things tells me it's got a lot of neighboring hydrogens. And I see 6 hydrogens here. Well, gosh, we can't put 6 hydrogens on 1 carbon. So the most simple solution is that we probably have 2 identical methyl groups. So with this, we've actually got quite a bit of information of what these carbon and hydrogens look like. So to put this together, the first thing I want to say is, well, what's on this side of the ester, on the oxygen side of the ester, and what is on the carbonyl side of the ester? So I'm going to look to the chemical shift. And the last piece here I didn't write is splitting. And we will use that to verify what's next door to what. So hydrogens that are on a carbon right next to an ester, right there by oxygen, I would expect to be down here around 4. So the chemical shift here, tells me that these 2 hydrogens are probably attached to the oxygen. So this gives me a really good idea that it is a CH2 that we have attached to this oxygen. Okay, and then if we look at the rest of the signals, we're going to have to build on the rest of this chain, because that CH2, that's not terminal. I do have 3 pieces that look like terminal pieces, right? CH3s are always going to end a chain. So if I look at that next CH3 group, it is a singlet, so indicating it has no neighboring hydrogens. So no neighbors. And it's also at a chemical shift of around 2. That looks like it might be next to a carbonyl. So I'm going to suspect that we have a CH3 group on this side of the carbonyl. And the fact that that's a singlet having no neighbors and these other signals all have splitting makes me think that they're attached together in some way on this side of the molecule where they could cause splitting. And so that brings us to the CH, and it's just a mess of peaks. Like, we really can't describe what's going on there. So split, but it's messy. So what we're looking for is that CH just probably has a lot of neighboring hydrogens. And the only other signal we have are CH3s, which are going to end a chain because they can only have 1 bond. So our only real choice here is to put the CH next. And now this messy splitting is starting to make sense because we've got it already next to the CH2 group, so it's 2 neighbors. And the only thing we have left to put onto this molecule are these CH3s. And if we pay attention to the CH3s, they are a doublet. So that means they're only being split by 1 hydrogen. So they are for sure next to that CH group or just attached to that CH group at the end of the chain. So now we have actually accounted for, let's make sure it fits our molecular formula. So 1, 2, 3, 4, 5, 6 carbon atoms. And we want to make sure we have all 12 hydrogens, which we should have because they were all represented in here, right? We have 6 and 1 is 7 and 3 is 10 and 2 is 12. And we place those all in the molecule. And then of course we have those 2 oxygens. And our functional group for our proposed structure matches our infrared. And let's check just even some of these simple things. So the number of signals. So if you look at this molecule, you would expect to see 1, 2, 3, 4 signals. So that's consistent. So let's label these signals. So I'm going to call these A, B, C, and D. And then that's really clearly indicate where these are on the molecule. So the 2 hydrogen doublet is these protons here. So we'll call those A. And this 3 hydrogen singlet at around 2 to 2.1 is by that carbonyl. So these are B. The signal C is that CH with a whole bunch of neighbors. As a matter of fact, it's got 8 neighbors, so we would expect that splitting to be fairly messy like that. So C is those signals. And then finally, this 2 CH3 groups for that 6 hydrogen doublet are these. So we'll say those ones are D.